and we've flown 9 of those so far of that version of the rocket that debuted just 3 years ago. Standing 18 meters or 59 feet tall, Electron is the world leader in its class for dedicated small satellite launch. Its black structure is made almost entirely from advanced carbon composite materials that keep Electron lightweight while maintaining the structural integrity needed to survive harsh aerodynamic forces of launch.
Yes, and what really sets Electron apart from traditional rockets is its revolutionary propulsion system. At the base of the first stage are 9 Rutherford engines with a single vacuum-optimized Rutherford powering the second stage. These engines are the world's first orbital-class rocket engine to be almost entirely 3D printed and powered by batteries. Its 3D printed design means a Rutherford engine's main structures can be made within 24 hours, which has been the secret sauce behind Electron's rapid scale since its debut in 2017.
All right, here's a breakdown of what to expect after those 9 Rutherford engines ignite for today's mission. From launch pad to delivering the iQPS to orbit takes just 9 minutes. Separation of QPS SAR-13 follows about an hour or so after liftoff. The total engine burn time for Electron's first stage is about 2.5 minutes long before the second stage separates and the vacuum version Rutherford lights up to continue the mission to orbit.
Now, across those next 6.5 minutes, we'll have a couple of launch milestones to get through, like fairing jettison and battery hot swap, before we see another stage separation event to send iQPS's satellite on its way to orbit on Electron's kick stage. Now, at that point, it's a quiet 40-minute coast phase around Earth for iQPS and the kick stage, before the kick stage starts its propulsion system to round out the orbit and deploy QPS SAR-13 to its 575-kilometer target altitude.
Okay, with a couple of minutes left in the countdown, we've got some time to tell you about one of the unsung hero products in our lineup of satellite components here at Rocket Lab. When we're not launching ourselves, we're finding other ways to help important missions get off the ground, and that includes one of the most exciting missions to head to space so far this year. NASA's Artemis II mission sent astronauts around the moon for the first time in 50 years, and every system on board the astronauts' Orion spacecraft depended on one constant: a reliable source of power.
And that power came from the spacecraft's 4 solar array wings attached to its service module, which was made with approximately 15,000 of Rocket Lab's advanced solar cells. It's an honor to contribute to such a groundbreaking mission, and we're excited to continue supporting NASA's Artemis program as it paves the way to greater lunar exploration and beyond. Here is more about the mission and the solar cells that powered it.
When NASA sends astronauts around the moon on Artemis II, they are venturing over 250,000 miles from home. In that deep space wilderness, every system on board the Orion spacecraft depends on one constant: a reliable source of power. That power comes from Orion's 4 solar array wings, the spacecraft's lifelines. These 7-meter arrays tilt and track the sun, but the real work happens in the solar cells that cover them: high-efficiency compound semiconductor solar cells. Integrated into these arrays are roughly 15,000 of Rocket Lab's advanced multi-junction solar cells. Unlike the panels used for power here on Earth, Rocket Lab's space-grade technology is engineered to capture more of the solar spectrum and to operate reliably in the harsh conditions of deep space. But in the vacuum of space, efficiency is only part of the equation. These solar cells are built to survive intense radiation, extreme temperature swings, and the mechanical stress of launch. At Rocket Lab, we know there is no margin for error. When these arrays deploy, they have to work, no exceptions. We are proud to partner with NASA and Lockheed Martin to enable the Artemis missions. By converting sunlight into 16 kilowatts of electricity, Rocket Lab provides the energy for Orion's propulsion, its thermal controls, and the air and water systems the astronauts depend on. As we help lay the groundwork for the Artemis era and the future of human exploration, Rocket Lab is honored to turn sunlight into survival.
The moment when Orion's solar arrays were deployed and our solar cells came alive for Artemis II was such a satisfying moment for our engineers and technicians who spent years designing, analyzing, testing, and building that technology. And with plans for a lunar base and more Artemis missions, we'll be putting more of that Rocket Lab technology to work to support human exploration deeper into space.
Today, though, conditions remain favorable and all systems are green for an on-time launch. Soon, Electron's autonomous flight computer will take control, managing the final 2 minutes of pre-launch checks and sequences independently. During this critical phase, the flight computer has the ability to pause the countdown at any time if it detects any data requiring further analysis. And at T-minus 10 seconds, our launch director begins the final countdown, guiding us to the moment we've all been waiting for, T0 and liftoff.
Now, we're just moments away from the start of the auto sequence where Electron systems take over. Let's tune into Mission Control now as the operators deliver their final callouts before launch. Go iQPS and go Electron.
And from now, there should be no red flags on your critical LCCs. Vcon LD in mission court.
LD Vcon.
Vcon, lock the auto sequence and confirm.
Locked.
Confirm all flight computer aspects are green.
All ESCOs are green.
Copy. We are go for auto sequence start at T-minus 2 minutes. LD is go for launch.
The vehicle is fully on internal power. AFTS is green and enabled for flight.
Box load is complete. System is in recirculation. Anti-geysering is disabled.
Stage 1 and 2 tanks suppressed.
High flow engine purge enabled.
T-minus 20 seconds and counting. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. But gonna proceed with immediate abort checks. GC, LD, in mission court.
LD GC.
GC, confirm the range state is inhibit.
Confirmed inhibit.
And confirm the stage 1 and stage 2 umbilical status are engaged.
Confirmed engaged.
And confirm no fires on the vehicle.
No fires.
Thank you. Vcon, LD, in mission court.
LD Vcon.
Vcon, confirm the abort auto sequence executed nominally.
This is Mission Control Auckland. As you can see, the vehicle has had an abort during the launch auto sequence. At this stage of flight, the vehicle flight computer is actively monitoring a wide range of vehicle performance parameters, and when any of these parameters are violated, the vehicle has determined it is not ready for flight and holds the count. An abort can be performed at any point up to the release of the vehicle hold down clamps, which normally releases a few seconds after initial engine ignition. Right now, the team in Mission Control is reviewing the data, so we'll stand by while we learn if we'll be able to make another launch attempt today with the remaining in-time window. As you've been watching and listening along, the vehicle's strong back has been resecured and the vehicle has been brought back onto external power. The vehicle has been placed in a safe state while the team reviews the reason for the auto sequence abort. Information on the next launch opportunity and webcast details will be shared on our website and social media feeds. Thanks for tuning in to today's launch attempt, and we are looking forward to seeing you again soon.